In the early days of Linux, back in the early 90s, users had to manually edit header files or run custom scripts to configure kernel builds. This became a little more systematized in the mid-90s with the introduction of config.in files that were parsed by Perl scripts. Then in the early 2000s, we were introduced to the Kconfig system that made the process much easier. This is both a configuration language and a set of tools used to enable, disable, and customize various pieces of software. When you have a massive set of libraries and drivers, such as the Linux kernel, having a tool like Kconfig is extremely useful for determining which parts you want to include in your build. Keep in mind that this is a somewhat older system that uses its own configuration language and a number of command line tools to get the job done. It's still used heavily in Linux kernel development and packaging, which is why Zephyr borrowed it to help developers include and customize software components. I'll show you the basics of Kconfig, how to customize options for your projects, as well as how to define custom symbols. Previously, we saw how CMake is used to include things like header files and source code, as well as generate the required files for various build systems. This time, we'll look at how Kconfig is used to customize your build by enabling or disabling different software components. If you come from the Linux world, this is probably old news to you, and you're welcome to skip it. If you have not seen Kconfig before, this is a good entry point to working with it. It makes up one of the foundational tools for working with Zephyr, along with CMake, the device tree, and bindings. To demonstrate Kconfig, we're going to enable the random number generator inside of our project. And this is going to be a software one, so it's not going to be very secure. In fact, you can see it's non-cryptographic here. All we're going to do is enable the random generator in Kconfig. That tells Zephyr to build and link the library for doing random number generators. We're going to use the system timer as our generator source. Once again, this is not for cryptographic use and just for tests. If you head to the Zephyr documentation page on random functions, you can see the types of random numbers we can get. It won't be fully random, so it's going to be pseudo-random, but that's fine enough for our tests. If you want to have true random numbers for things like encryption, cryptography, and whatever, then you will want to enable the entropy interface. In many cases, this means you need to connect specialized hardware that generates random bits so that you can get true random numbers. The ESP32 has a true random number generator on it, but you have to enable it in hardware. It's usually a bit slower, and it means you have to do stuff in the device tree, which we will cover in the next episode. So if you want a challenge after you learn about device tree stuff, come back and see if you can connect the ESP32 hardware entropy generator to the random number generator and get that to generate true random numbers. But for now, let's stick with the simpler pseudo-random number generator. If you've been following along, you should have a Docker image created with the Zephyr environment for our ESP32 development. I've gone ahead and fired up that server, and I've already connected to it with my local VS Code installation. If you'd like to see the source code for our random number generator, go to Zephyr, include, in Zephyr directory, go to random, which is right here, and you'll see random.h. These are the Doxygen comments that get exported and generated into that web page we were just looking at. But you can take a look at all of the calls here to generate random numbers, like 8-bit, 16, and 32-bit random numbers. Let's close this, go back to our applications. Let's create a new folder in here. I'm going to call it 03 Kconfig demo. Unlike our previous applications, there's no need for a boards demo because we're not connecting any hardware. If you want to come back and connect the true random generator, the entropy hardware, in the ESP32, feel free to do that, but you will need to create your own overlay file for that. But for now, let's just do everything in software, even if it's not great random numbers. We will create a source folder, and in that source folder, we will create main.c. I will start off by including the random header file that we just looked at. And by the way, If you want to take a look at some samples, go into the source directory for Zephyr. There's a whole samples directory here that has lots of really good samples. They may not have them exactly for your board, but it's a good starting place to take, modify, and use for your own purposes. I recommend starting off with this really simple hello world. And then if you go into basic, there's things like Blinky, fading, how to work with GPIO. And if you go into drivers, crypto, you can see some examples here. But let's go back to our application and make our own app from scratch. So with main.c, we've included that random header. Just like we had in our Blinky example, we're going to sleep for 1,000 milliseconds. We're going to use the random 32-bit generator to generate random 32 bits, and we're going to store that in an unsigned integer that's 32 bits wide. In our forever loop, we are going to just get a random number. That is the sysrand32get function. If we go back to our documentation, go to our random, you can see sysrand32get. That is the function we are using. You'll notice here it does indeed return an unsigned integer that's 32 bits wide, and it just basically randomly sets those bits for us. Let's go back to our code, and we're just going to print k that value. Notice here that I'm using the %u, which says to use unsigned integer, and then that's just going to get filled in with whatever that random value is. Then we're just going to sleep for 1 second. We're going to use that kmsleep that comes with Zephyr. And Zephyr, like Linux applications, likes things to return with 0 even if we never get there. That's just standard Linux practices that got carried over to Zephyr. In the top level directory for our Kconfig demo outside of source, we're going to create a new file, and we're going to create our cmakelists.txt, just like we did in the previous episode. And if I remember, oops, we want to use 3.20.0 because that's the version that Zephyr specifies in all of their samples. In fact, we can go look at that. When we search for it, we saw it in the last episode. If we go to, I don't know, basic Blinky CMake lists, sure enough, there it is, 3.20.0. We're just going to copy that and use what Zephyr uses. Next, we're going to tell CMake where to find the Zephyr package. That includes all of the specialized CMake stuff for us, including the CMake extensions. We're going to say that the package is required, and we're going to tell it to look in the Zephyr base environment variable, which should be set in our system. We're going to give our project a name. We're going to tell it where to find our main application source code, and we are going to say that this source belongs to this target. Remember that Zephyr automatically creates an application target for us called app. And so anytime we apply source code or link to app, we have to use that name. Let's save this. Let's go back, make sure that our main.c is saved. In that folder, we need to create prj.conf. This is absolutely required by Zephyr. It will look for a file named this in your application folder, even if that file is blank. This is going to be where we store project-wide, or in our case, application-wide, Kconfig settings. So if you need something to take effect for the whole application, we would store it here. But for whatever reason, Zephyr requires you to have this file, even if blank. Next, let's go into our 03 Kconfig demo that we just created. Then we're going to call west build-p means pristine. It's going to clear out any build folder that we might have. I like to use always just in case, but you can use something else like auto there. -b to specify our board. We also need to specify the SoC, which is the ESP32S3, and the processor or CPU we're targeting, which is the Pro CPU. Notice there is no need to specify an overlay file here because we're not connecting any hardware like we did with Blinky. We're just going to do everything internally with the system using software libraries. Give it a minute and let this build. Uh-oh, this was entirely intentional. You will notice that this build fails. If you read through the error messages, you will see something like this, undefined reference to z implement system rand get. That's kind of confusing. That means that it can't find, if this is a function or a variable, it can't find that reference. And it's something to do with random.h. Even though we included the library right here, this library hasn't been enabled. To do that, we actually need to use Kconfig to essentially turn on the library and any dependencies that library requires so that Zephyr knows where to find it, where to build it, and then it will build it and link it with our main application. So we need to learn a little bit about Kconfig to make that happen. Kconfig is a series of usually yes or no or numerical values to enable or disable various software components. If you go to the interactive Kconfig interfaces page for the Zephyr documentation, you will actually find some really good information about both Menuconfig and GUIconfig. Both are, I would say, graphical interfaces. Menuconfig actually works in the command line, and GUIconfig you need like a Windows system to make happen. These guide you through the process of searching for and enabling or disabling various symbols within Kconfig. Feel free to read through this. This is what Menuconfig looks like, this is what GUIconfig looks like, and because we are not using a graphical interface, we're going to do everything through Menuconfig. We're going to take a look at this to enable our random number generator system, but know that this is fairly powerful, and it can really help you find symbols to enable to make your software work. If you go to the Wikipedia page on Menuconfig, it actually has a really good reference guide on how to navigate in Menuconfig and how to search for various things and what the various symbols mean, because it can be a little overwhelming at first. So let's go back to our system here and let's fire up Menuconfig. To do that, we're going to call the same West build. We're going to say pristine always to rebuild that build folder, and we need to specify the board, and that's because Kconfig will compile all of the default enabled settings for our SoC and our board, pull that into the build folder, and then we're going to do -t Menuconfig to start up Menuconfig. So it's going to create a set of default settings for us based on that board, based on what was set for that board by, say, Zephyr or Espressif, and then we can modify it to our liking in order to, say, enable the random number generator library. And here we have Menuconfig. So I'm going to bring this screen up a little bit so you can see what I'm doing in the terminal here. You can use the arrow keys to navigate through the various options. Think of this like folders or a tree. I can see modules, I can press enter, I can see the various options within modules. You can see things like brackets here. I can press spacebar to enable or disable this. Sometimes you'll get additional options. I can press enter, go into that. I can adjust my settings here. I can press escape to quit, and I'm going to disable LVGL support because that is not something we're going to look at right now. So let's press space, I'm going to press escape, and now we're back at the top level. Finding what you're looking for in here can be kind of difficult. Luckily, Menuconfig gives us the option to search for things. If you look down here, you see this / jump to symbol. Reality, that means search. So I'm going to click / and I'm going to bring up this search bar. It uses regex in order to search for these symbols. What we want to do is search for something that starts with random. All these look pretty decent, but what we're really looking for is something like random number generators. Notice that sometimes you have to read these or go into them to learn more about them. So let's select menu random number generators with our arrow keys. I'm going to press enter to go in here. Take a note of the breadcrumbs at the top. So if you're at that top level menu, you now see how to get to this going through subsystems and OS services. Once again, think of that like as a folder, and then going into random number generators to get to this configuration screen. Right now we cannot select cryptographically secure random number generator because that has not been enabled. If you can select things under this submenu, this would end with an arrow, but because it ends with just that bar, hitting enter or space, which I'm doing right now, does nothing. If you see it ending with an arrow, that means you can press enter and go into that submenu. But let's select allow non-random number generator or pseudo-random number generator and press space. That is going to enable that function for us. Now you see both of these actually have the arrows. We can go into here, but this is saying use insecure random number generator for testing purposes, which is fine. That's already selected for us with that X. So let's press escape, go to random number generator, press enter to go in here, and once again, you see we don't have many options. It's already been selected for us. What's neat about these symbols is you can type question mark, which you see this down here, and that gives you information about that symbol. It shows you the value, what's been set. So in this case, it's Y, yes, for enabled. You get a description. You can see that it enables the random number generator based on the system clock, which is not truly random and mostly just for testing, playing around, tinkering. Don't use it for cryptographic stuff. If you scroll down, you can read more about the dependencies, what needs to be enabled in order to make this work. And you can actually see where this gets pulled in from. Press escape to get out of that information page. If you press A, you can see all the other options that are not available to us. They will be highlighted in red. So if we enabled the true hardware entropy driver, we could actually configure these and use them instead of our system timer. I'm going to highlight this, and you can read about the entropy driver. So to make this work, you need to search for that symbol. So let's do entropy has driver. We can click on that to go here. You can see that's also red, but we can type question mark to go in here. Notice at the top there is no prompt key here like we saw in some of the others. This means that this value is not meant to be set by the user. But if we look at the direct dependencies, you can see that entropy generator needs to be turned on. So let's search for that. Press enter. You can see entropy drivers here. You can press space to enable it, press enter to go into the menu, and if it's not already, you can push A to see the various possibilities. The red ones you can't select. So let's filter those out. You can see an ESP32 entropy number generator. Looks like this has been newly added to this Kconfig. And because we enabled that entropy driver, this is enabled by default because we're using an ESP32. Now, let's search for entropy has driver again. Question mark to view that, and you can see that this has automatically been set. Even though it has no prompt, whenever the dependency is set, this gets automatically set to yes. So now let's search for random. Let's go to our random number generators. I'm going to push A to filter those out. Let's go to random generator, and you can see that we have other options. So use entropy driver is now selected as the default. You can actually push space to select it. You can see that it dropped me out of the menu when I did that, but it allows me to select that, and you can see that selection here. Use entropy driver. We can go in here. Set system timer is now the selection for this submenu. Even though we have enabled this in software, we would still need to enable the hardware entropy driver for the ESP32, which requires doing some custom device tree modifications, say in an overlay file. We're going to get into device trees in the next episode, so feel free to come back if you want to play with true random number generators. Since we don't want to use that, I'm just demonstrating how to navigate Menuconfig. Let's search for entropy generator, which is right here. Let's press space to disable that. In fact, you can hit question mark. You can see that, hey, look, it has a prompt, which means we're meant to do it as a user, and it's now been set to N, which is no or disabled. We'll search for random again. We will select our menu, random number generators. And you can see the random number generator has been set to the system timer clock. If you go into that, that's the only option we have. Even if you hit A, view all the others, that's the only option. So let's hit escape to get out of that. And you can either press Q or press escape a bunch of times. It will ask you to save your configuration, Y for yes. And that is automatically written into our Kconfig demo, build. Let's go into Zephyr, and there should be this .config file. This is where all these things are saved. Let's drop this terminal down so we can see what's going on here. You will notice that all of the symbols here start with config underscore. That's just the way Kconfig looks for symbols. Everything starts with the config prefix. Kconfig, unlike YAML or CMake, has its own syntax. In this case, you will generally see the symbol in all caps, equals, and then the value. In this case, this is a numerical value. This is a hex value with 0x some number. Y means enable. You can also do N, that means disable, but the convention is to not set it. Either comment it out or just not set it. And that means that that particular symbol is not set. That allows you to do things like if define in your preprocessor in, say, your code. to look to see if a symbol is set or not. Let's search for entropy. But if we search for, say, random, you can see where we enabled the test random generator. This sets the initial state, so that's kind of like the seed. You're welcome to play with that. And it enables the timer random generator, which gives us those pseudo-random numbers. These are the things we just changed in config. They get saved into this .config file, which first of all pulls in all of the default settings from our board, our processor, defaults in Zephyr, and then it updates the changes that we created in Menuconfig or GUI config if you're using that. If you want to see some of those, let's go to our Zephyr RTOS source code. We'll go to drivers. I believe this was the entropy folder. And you should see Kconfig ESP32. This is the specific generator used for the ESP32. You can also go to, let's see, SoC for our system on chip. Let's go down to Expressive. You'll see our ESP32S3. All of these Kconfigs are different fragments, and that's what these different files are known as. When you see config like this and then a name, this is creating that symbol. So this is how you create variables, which we will look at in a moment. You also have the default configuration file, or defconfig, which sets up some default values for us, and that's for the ESP32S3. If we want to go to the board level, we can go to boards. Let's take a look at Expressive. We'll go to the ESP32S3 DevKit C, that's the board we're using, and you also see some additional Kconfigs here that either define custom symbols or creates some defaults for us. Whenever you see these defconfig, these are default configurations, and since we specified the Pro CPU, Zephyr pulls in this fragment to set these values for us, either enabling things or setting this, say, stack size. Once again, we can modify those using something like Menuconfig, and they get updated in this .config in our build folder. When we go to build this application, this is the file that gets read as the ultimate amalgamation of all those different fragments, including our custom settings. There's a problem with this, and that is, remember that build gets overwritten or deleted every time we create a new build, unless you use that -p, say, auto. But since we're using always, this build folder gets blown away, and so does our config. So anytime we use Menuconfig, we no longer have those settings. So we need to find a way to save these settings. For example, if you use west build -p auto, it will save those settings for you. But since we're using always, that's not good. That will destroy those settings. One way to save those is to say, let's put them in prj.conf or something unique to our board. And we can just store that in the boards folder. But how do we know which ones we've changed, and how do we know which ones were dependencies that we didn't manually set, like the ones we saw here? Luckily for us, anytime we make a change, .config gets updated, and the previous one gets saved in .config.old. That means we can do something like diff both of those files. Diff has its own shorthand for things, so you will see things like the original line, so .config.old. Things were added with this A to lines 588 and 589. So the arrow means coming into this second file, so coming into this new .config. We don't set stack canaries, and we set the stack pointer. That seems like some dependency that got set whenever we enabled the random number generator. C means changed. On this line, it got rid of this symbol, test random generator, so it was not set initially, and it changed it to equals yes, so it did set that value. Then on 1144, it added this A, these two lines. So it enabled test random generator and test CSPRNG generator. Those are the things that are necessary for us to include the random number generator library that's in Zephyr. One way to think about this is Kconfig generally handles managing software and libraries, whereas device tree is used for things like connecting hardware. Together, they make up the primary systems that we can add or remove modules in Zephyr. And the same for Linux kernel development or module development as well. Diff is great for basic texts and comes with most Linux installations. Zephyr also comes with its own Diffconfig tool that's in scripts. It's a Python tool, so we need to call Python, go to the Zephyr folder, and then scripts, Kconfig, Diffconfig. Like we did with diff, we need to point it to the old file and the new one. I actually find this one a little bit harder to read because it says, oh, test random generator went from no to yes, which actually means it got rid of the comment, enabled the symbol and set it to Y. It created a comment that said config stack canaries, which is the same as setting it to no, set the stack pointer random value to 0, which you see here, and enabled these two symbols. I actually like diff a lot better because it shows me what actual lines changed. But you have both options. With these in mind, we can take it to our prj.conf. Remember this file that we created, Zephyr requires this file even if blank. So one thing to do here is I'm just going to take the output of my diff, I'm going to copy that, I'm going to paste it in here, and I'm going to just get rid of these diff comments. So we end up with the actual lines. Remember that this means outgoing, so this is no longer correct. This dash 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 means the difference between the first file and the second file. So we have the incoming symbol here. We can get rid of this line nomenclature and we can get rid of the incoming. So we end up with something like this. Go ahead and save this. And let's call that West build again. Notice I'm not doing the T menu config. I'm actually going to build the project this time. Zephyr by default looks for this prj.conf, reads it in, and uses that to update the .conf file in the build directory. So let's let this fully build. Once that's done, scroll up, you'll notice that this says don't use the timer random generator for things like encryption. That's all. We knew that. Let's, not save that. I'm going to close out that original .config file. Let's open up the new one in our build directory. Sure enough, these are the same. We have enabled these. Let's close that down. I don't need the Makefile Tools extension. That's fine. There is one problem with this, and there's a reason I don't like using prj.conf. If you have certain things that you need for all of your boards, that's great, but you saw a couple of symbols in there that were ESP32 specific. If I tried to put that in here, and I tried to enable it for, I don't know, a Nordic board or something else where I want to enable the entropy generator, that's going to be a problem because that doesn't have that symbol. The symbol might be set, but Zephyr's not going to know what to do with that. So while this might work for most of your boards and would work for a general project, if you have board-specific stuff, it's usually a good idea to put it into a boards folder. In addition to creating a unique boards folder, you could also do things like new file, prj, say release, so you have a release configuration. You could put your things in here. You could do your build command, and you can use the symbol conf file equals prj release.conf. This says to overwrite the default of using prj.conf and use this release.conf instead. So this is how you would create various debug release configuration files for your project. But since we want to do it for a board, let's create a board-specific fragment file. So where we would keep our overlay, let's create a new boards folder. And we're going to create ESP32S3 devkitc.conf. I like to give it the name of the board and then .conf, much like you would do for the overlay file, so that a user would know to include those if they're building for a specific board. Let's go back to our prj.conf. I'm going to cut these symbols, save this file, paste them into my board, save that one. Let's get rid of this release, so I'm going to delete that. Yes. And you notice prj.conf is now blank, and now all this information is in my board-specific fragment. Now let's go back to where we built the board again, not with Menuconfig. And instead of passing the conf file, you could pass the conf file if you want to do, say, a specific release, but without specifying that, it's just going to assume the prj.conf. But we can also say extra conf file, so it pulls in that fragment in addition to whatever specified in prj.conf, or if we specify the specific release.conf, those symbols get pulled in as well. So let's go ahead and flash that and give it just a moment. Feel free to check that .conf file again if you want to make sure that your symbols have been set. Here they are. And now let's try to flash this to our board. So come over to our terminal. We don't want to end this because this is our server. Let's create a new prompt. Go into the directory that's the repo for this course. Don't forget to activate your virtual environment for Python. If you're on Windows, that's calling the activate script. If you are on Linux or Mac OS, that's going to be something like source then bin activate. But since we're not on that, we don't need to call that. You should see venv in front of your command prompt. And then you will want to use ESP tool to flash your board like we've been doing in the previous episodes. Make sure to point it to the 03 config demo build Zephyr zephyr.bin and wait a moment while it connects and flashes your board. Like we've done before, use the PySerial mini-term tool to connect to the board. And with any luck, you should see random values being printed to the terminal. Hopefully this helps you understand how to work with Kconfig to set various symbols to enable things like software components and libraries. But what if you're creating your own library and you want to create your own Kconfig symbols for people to enable or disable? Let's talk about how to do that, and I'll show you an example. Let's clean out our workspace here. I'm going to close these files, and I'm going to close all of this so you can see where we are within our workspace. If you remember from the previous episode, I challenged you to create your own library. Now we're going to take that library and we're going to encapsulate it in a Kconfig symbol so that people can turn off and on the library using Kconfig. Let's have a modules folder. Notice it is separate from our apps. This can be really anywhere on your computer. I just liked it in the workspace. This is known as an out-of-tree module. A lot of times Zephyr wants you to create modules in the Zephyr code. So the idea is you would fork Zephyr and then create your own custom module here and then use something like West to keep all of this up to date. But to keep this simple, we're just creating modules in some random directory. Well, hopefully it's a directory mapped to our host system if you were using the Docker image. But in here, we're going to create a new folder and we're going to create the say hello folder in that. This is going to be our library. Let's create our header file, and I'm just going to paste it in. This is from the challenge of the second episode where we create a library, and I'm just going to create this public function declaration. Let's save that. We're going to create our source code. I'm also just going to paste it in. We need to include our kernel here so it works with Zephyr, and we get this print k option. And we include our header file, and we're just going to say hello to the main screen. Let's save that. From here, let's create our Kconfig symbol. So let's create a new file. This is often called Kconfig with a capital K. Defining Kconfig symbols is a little different than just setting them. If we go back to our Zephyr reference documentation, there's a whole section on Kconfig. I recommend looking through these or using them as a reference if needed. This tips and best practices is a really good guide for writing your own Kconfig symbols. You will notice here that we say config to create a symbol, and then we define a bunch of settings underneath it. Indentation doesn't really matter, but for readability, you will often see a tab or 4 spaces underneath config to let readers know that these settings are part of this symbol. So let's go back to our code and create our own. We're going to create a symbol named say hello, and we do that using the config keyword space and then the name of our symbol. Notice that say hello is in all caps. While I don't think it's required, pretty much every system that uses Kconfig, including Zephyr, by convention uses all caps for symbols. Next, we're going to define this symbol as a Boolean, so it needs to be set as yes, no, or basically undefined, which is the same as no. Then we'll set the default, we'll set it to no for disabled. And then we're going to set one or more depends on, which means it needs to be dependent on another symbol being enabled, in this case, print k, which comes from the Zephyr system. I'm also adding comments with the # or hash marks just to make it a little easier to read when you go back through this code. The help just tells the user a little bit about the symbol. In this case, we're just going to say adds the say hello function. Let's save this. And we need to tell CMake how to build our library. So we're going to make a cmakelists.txt. The first thing we're going to do is to see if the say hello symbol, remember it's prefixed with this config underscore, if that is set in our Kconfig system, then do the rest of this CMake stuff that we're about to type in, which is going to say, go ahead and build this library. Otherwise, skip building the library because we don't have any need for it. This is what allows us to make a modular system. So we're not building Zephyr and all of the Zephyr modules and libraries every time we build a project. We're just building the stuff that is set in Kconfig, and this is the magic that allows that to happen. Zephyr has some custom CMake functions when we include that package. One of them is this Zephyr_include directories. This helps Zephyr know where to look and helps Zephyr build this library for us so it gets included automatically in our application or our project. The first thing we do with Zephyr include directories is to include the directory with the header files or the .h files. That helps our source code, our application code, know where to find that header when we do that #include. Next, we add the source file that we want to compile for this library. We're going to use the custom Zephyr library sources function and point it to the sayhello.c file to say, hey, let's include these files and tell Zephyr to compile those and create a library from them. To close out that if statement, we just use end if, and that's a normal CMake thing. Let's save this file. In many cases, this is all you would need to create a basic library that you can control and say turn it off or turn it on using Kconfig. Zephyr adds a little something else to this. Zephyr doesn't quite understand what this is, it's just some files. We need to tell it that it is a Zephyr module, and Zephyr knows what to do with a module. In this case, Zephyr looks in a module folder for certain things like a Kconfig file, CMake lists, and it knows what to do with those in order to build and link to our library. So a lot of stuff is happening on the back end for Zephyr, but we need to tell Zephyr that this is a module and you should treat it like a module. To do that, we are going to create a new folder. We're going to call it Zephyr. The naming here is very important because when I point to this say hello directory and I say, hey Zephyr, treat this like a module, Zephyr is going to go, oh, is there a Zephyr folder in there? And in that Zephyr folder, is there a file called module.yaml? These file names are very important. The only difference I think you can be .yml instead of .yaml, but know that the naming is important here. In addition to C, and now C++ and I think Rust, Zephyr loves to have a variety of configuration formats and syntaxes. We've already seen device tree source using our overlay file. We've looked at CMake, which is a different syntax. We have Kconfig, which is its own syntax. And now we're introducing YAML, which is a completely different syntax for defining different variables and settings. So part of the fun of Zephyr is learning all of these different syntaxes. If you've never seen YAML before, it's fairly common in a lot of configuration files for build systems and for things like Docker Compose if you're trying to spin up multiple Docker images. It's a fairly modern syntax, and it's not too bad to read. This site, this spacelift.io/blog/YAML, has a really good primer on YAML if you haven't seen it. In essence, it's kind of like JSON or Python dictionaries. It's just a collection of key value pairs. Here you can see a key, company, and you can see the value, spacelift, that belongs to it. You also have arrays. So instead of brackets like you have in a Python dictionary, you have these dashes indicating elements of that array. So domain is an array with DevOps and DevSecOps. Like Python, indentation matters here. So you see that this is one tab away, but it's space dash space. And that says that it is underneath tutorial or a value within the tutorial array. YAML is its own, in essence, dictionary with these keys, name, type, born, and then this creates an array under tutorial. And we have some basic key value pairs down here. Lucky for us, our module.yaml file doesn't need to be very complex. The first thing we need to do is set up a name. Zephyr is going to look for this name key, and it's going to name the module say hello. While I think you can use 4 spaces here, YAML seems to want to use 2 spaces for a level of indentation, so I'll go with that because that seems to be the Zephyr standard. And we're going to say CMake dot. So these key names are important for Zephyr. So this says during the build system, it's going to look in the current directory, which in this case is not in Zephyr. It's actually one up from the Zephyr folder. So in say hello, look in that directory. That's the top level or the root directory of our module for cmakelists.txt, which is here. If you specify something else, that cmakelist.txt should be in another folder wherever you specified here. And then we tell it where to find the kconfig file to read in as a fragment to include during the build process. In this case, look in the top level directory. Remember, we specified that it is here in say hello, and look for the file called kconfig, which we made here. Make sure that these names match. Go ahead and save that file. And let's go back into our application. So let's get rid of these module files. Everything should be good to go there. Let's go to our kconfig demo. Let's go to our application code. Now we need to include our library. Let's move this terminal down. Like we saw with CMake, we don't need to specify the exact location of this header file. We'd have to go up and out to modules and go into say hello. Because we've turned this into a Zephyr module, we can just specify the header file that we defined here in modules, and Zephyr knows where to find that because we've made it into a module, and CMake knows where to find that once we've included all of these Zephyr extensions. After our random number, let's just call say hello. So now we should get a random number, and it should print something to the console that we've defined in our say hello module or library. Let's save this. We also need to go into our application, CMake lists, and this is important. Before find package, this is where we define our custom out-of-tree modules. Remember how I said that Zephyr knows what to do with that module and it gets built and linked properly? This is where we make that happen. So we set a variable, in this case the Zephyr extra modules, and we're going to set it to the current directory, wherever our CMake lists file is. We're going to go up to, so that's to apps and workspace. We're going to go into modules, which is modules, and we're going to look for say hello. We're just going to point it to this directory. This variable means something to Zephyr when we call find packages. This is going to initialize the Zephyr package. It's going to look at this variable and know that you can add more than one external module here. It's going to find the modules. It's going to look in that directory, look for a Zephyr folder, look for a module.yaml file, and it's going to create this into a Zephyr module that we can now include as a library in our application. Let's go ahead and save this. Let's bring up our terminal. We're going to call West build and bring up Menuconfig like we've done before, but we are going to go ahead and add our extra conf file to make sure that those kconfig settings are the way we set them from the previous example where we enabled the random number generator. With Menuconfig up, let's search for say hello, and there is our custom symbol in Menuconfig. Press enter to go there. Notice that it is basically under top, it is a custom module, or it's in the modules, and there is our custom symbol. We can press question mark to read about it. You can see that this was derived from our kconfig file, and you can see all of the information that we set here. It is a type bool, it defaults to no or off, and here's the help that we wrote. And here is the dependency. Since print k is enabled, we are allowed to enable this symbol. Feel free to read about it here. You can see where the actual file is located, which is sometimes quite helpful if you need to go read that kconfig. Press escape to get out. You are welcome to set it here, but remember that's not saved every time we build, because if we blow away the build directory, that gets deleted. So I'm actually going to keep that unset. I'm going to hit escape or press Q all the way out. I'm going to say no to not save my configuration. And we know what that symbol is. That means we can go into our boards or prj.conf and we can add it here. We know that the prefix is config, and we know that the symbol name is say hello equals y. Save that, and we've just enabled our say hello module. Let's go to a previous command. We're going to delete this Menuconfig, and now we have the command to fully build our application. With this done, go ahead and bring up our terminal. Remember that we can press Control close bracket to exit out of the serial terminal. Go up, let's flash this again. And if we press the arrow key up, we can go to previous commands and let's open the serial terminal. And sure enough, we have the random value followed by hello. That means this is working exactly as intended. Let's Control close bracket to exit. We'll minimize that. And we are almost done, but before we are, I want to show you a couple of interesting things. If you go into the build directory, if you go to Zephyr, and let's take a look at our config just to demonstrate this. Sure enough, there is our custom symbol. And it looks like Zephyr added a module symbol for us that gets automatically enabled when we enable this symbol. This is Zephyr doing its thing here. Let's close out of that. Back in the build directory, you go to Zephyr, include. There's going to be a generated folder in there. If we go into Zephyr, yeah, this is getting pretty deep now. Go to autoconf.h. What you will see is that Zephyr has generated custom preprocessor definitions for all of our symbols. And in fact, we can look for say hello, and we can see it is defined here as 1, which means enabled. You can also define strings or values if you want, but 1 means basically it's enabled. That definition exists. If you go back to our board configuration file, let's set this to no, or if we do this the proper way where we set this to Y and then comment it out, that basically sets that to no, because remember the default for that symbol is no. Make sure you save that file and try to build again, see what happens. You should, in theory, get a fatal error. Say hello.h, no such file or directory. And that is in our application main. It's on line 3. So let's go here, and you will see the build system does not know where this file is. Now, why is that? That's because we disabled that symbol, and in our CMake lists, the header files only get included if that symbol is set. That's a problem, which means that this code only works or only compiles if that symbol is set. If you want to make truly modular code, guess what we can do? Remember in that autoconf.h file, this symbol gets defined for us by Zephyr whenever we build, which means this symbol exists for us in our code, and we can do some slick preprocessor settings like if this symbol is defined, then you include this, and then close that out. So now this is conditional on our Kconfig symbol being defined. We need to do the same thing for our say hello function, because this function doesn't exist without this header file. So I'm just going to paste that in there, and then I'm going to say and if. Now, let's try to build again. What do you think will happen? Ooh, it looks like it built this time. So what happens when we flash it? So let's go back to our host system here, where we can flash it. I'm going to flash it to my board, and let's open up a serial terminal. Sure enough, it is not saying hello anymore because we have disabled that symbol. We have written modular code that doesn't do this portion if that symbol is not set in Kconfig. If you head to interrupt.memfault.com/blog/practical_Zephyr_Kconfig, this is a fantastic article written by Martin that gives you a primer on Kconfig for Zephyr. It covers a lot of the stuff and more of what I just showed you in this lesson. I recommend using this as a written guide that supplements what I talked about and what I showed you. Now for your challenge. Let's go back to our code. This function here, ran32get, gives us random 32 bits. You can imagine that the bits are either 0 or 1, just kind of randomly distributed. In theory, this should give us a random distribution between 0 and about 4.3 billion. Feel free to keep the config say hello here if you want, but what we want to do is go into here, and we're going to create a double random float. That's going to hold our random number. The issue is this isn't particularly useful if you want to say, give me a number between 0 and 1 or 0 and 10, and you can include decimal values. So let's turn this into a float. We're going to take that 32-bit number, we're going to cast it into a floating point number, and then we're going to divide it by the maximum value for a 32-bit number, plus 1, so it's no longer, what is that, hex, FFFFFF, whatever. It goes up to that 100000, and that's the actual number of values possible in a 32-bit unsigned integer. Then we're going to change this print k. We're going to say print k random number 0.3f. This will print out a floating point value rounded to 3 decimal places. instead of the 32-bit value, we need to use the float. Go ahead and save that. Let's build it. When that's done, go back to our host terminal, control close bracket to make that stop. Press the up arrow key to go to a previous command. Let's flash it because we just modified that file. And open up the serial terminal. Wait, what? It just says float. That's not a number. Okay, what's going on here? Print K means print kernel. This is a fast, no buffering implementation of printing something to a console. It has fewer features than printf, which you're probably used to if you're coming from C or C++. Printf is often used for user space or user applications. Print K is useful for things like from the kernel, and embedded systems and Zephyr likes you to use this because it's often faster and takes up less space. However, floating point formatting is often disabled on many embedded systems, as processing floating points, especially for printing, takes up a good amount of resources. Your challenge is to figure out how to print floating point numbers. So instead of seeing that star float star, make it print an actual floating point value here. If you look at the datasheet for the ESP32, specifically the S3 that we're using here, go down to the feature list, you will see that there is a single precision floating point unit. That means that the ESP32 is capable of handling floating point numbers in hardware, and it's going to be a lot faster than trying to do it in software. You can enable this using Kconfig. The other option is to use one of the standard libraries. These are the ones that come with Zephyr. They implement many of the standard C functions that you might be used to, like string manipulation, memory management, some extra math stuff. The Common C library is a wrapper that provides a common interface to the other libraries. Minimal libc is lightweight and the smallest resource usage. newlib is a more complete C standard library. It has the largest resource usage. And then there's picolibc. It's lightweight, but more functions than minimal libc. Some of these support floating point operations and formatting in software. Let's go back to our code. And we're going to go to -t, Menuconfig, and let that fire up. In Kconfig, if you search for picolib, press enter. Here are your options that we just looked at. If you type $? on picolibc, you'll see that it is the one that is enabled by default. And while it is enabled, there is another symbol that you will need to search for and enable if you want to print floating point values using software. Or you can figure out how to print them using the hardware floating point unit, or FPU, instead. I leave that up to you, and good luck. If you set everything up right, when you enable the serial terminal and look at what the ESP32 is printing out, you should see the numbers being printed out in decimal format like this. If you get stuck, there is a solution in the GitHub repository, but I recommend trying this on your own first so that you get a feel for how Kconfig works. Good luck with this challenge. If Kconfig is still somewhat confusing, don't worry. We'll continue to use it in various samples throughout this series. In the next episode, we'll start tackling the device tree, which I honestly found a good bit more complex than Kconfig. In fact, we'll spend several episodes on it, building up to writing our own device driver. Stay tuned.